In this video, we're going to look at a shifted paraboloid, and we're going to try to find a parameterization and the standard normal vector. So let's start with the sketch, even though I'm not sure that sketch will be the most helpful thing in the world. But what we have here is we have an x on one side. So I know it's a paraboloid because I have x equals something squared plus something squared. It's technically an elliptic paraboloid, and it will, in fact, have ellipses, but I don't care about that too much right now. Since the x is by itself, I know that it's going to be kind of circled around the x-axis, and because there's a 5 plus in front, I know that it's going to be shifted 5 up. And then from there on out, we're going to just have this little kind of cone, well, not cone shape, more like a bowl shape going outwards. And that, of course, goes all the way around. So that's kind of the shape we're looking at here. And we want to find a parameterization. And once again, we have a lot of circles, or technically ellipses, which is kind of keyed in by this fact that we have y squared plus z squared somewhere along here. So since we have this y squared plus z squared in there, let's go ahead and start by kind of just taking a guess and saying that we'll probably want my y to be something like cosine of t, and we'll probably want my z to be something like sine of t. And we'll probably have other stuff to fill in there as we go, but that's a good place to start. So if I plug this in right as is, then if I plug in cosine of t, sine of... one other thing. Before we even play around with that, notice that we once again have circles of a bunch of different sizes. We have small circles over here and bigger circles there. So since that's going to depend on another parameter, let's put an s there right now because we know we're going to need that. Okay, so we have bunches of circles of different sizes. If I just plug in these to the right-hand side, I'll end up with something like 5 plus s squared cosine squared t over 9 plus 4 s squared sine squared of t. And what I'd really love is for this to just be a cosine squared of t, or maybe an s squared cosine squared of t and an s squared sine squared of t. That would be really nice. So let's see if I can do something to kind of make that happen. Well, if I put a 3 up here, that will kind of give me a 9 up here that cancels out with my denominator. And if I put a 1/2 here, this will give me a 1/4 that kind of cancels out with that 4. So now, if I have this as my parameterization for x and y, this will turn into 5 plus s squared of cosine squared of t plus s squared of sine squared of t, which is 5 plus s squared. So that's really nice. And so that kind of tells us what we probably want x and y to be in my parameterization, or sorry, what we want y and z to be in my parameterization. What do we want x to be? Well, since this is a parameterization, I want, when I plug these things in, I want them to be equal. So on the right side, when I plug in y and z, I get 5 plus s squared. On the left side, when I plug in x, I also want to get 5 plus s squared. And the easiest way to do that is to just let x be 5 plus s squared. So now if I plug in that for x, and I plug in these for y and z, I get the same thing on both sides, and we're good. I'm going to make a quick note. If you had forgotten to put these s's in here, you would have probably ended up with something like 6. You would have ended up with 6, something like 6, 3 cosine of t, 1/2 sine of t. And that's nice. That's all well and good. That's actually only one of these circles on this, or one of these ellipses on my paraboloid. So it does satisfy the equation because it's on the paraboloid, but it's not the whole thing. That's why we need to have the s to make sure we're getting the whole thing. Speaking of getting the whole thing, let's think about what we need our s and t values to be. As always, since t is representing some angles, we probably want it to go from 0 to 2 pi. And this, I actually didn't even tell you how far s is going, or how far x is going, so it doesn't super matter. But if we said maybe something like from x equals 5 to 10, well, then we'd see that we need 5 to be less than or equal to 5 plus s squared is less than or equal to 10, which you can play around with and see that s needs to be between 0 and it would be square root of 5. So I didn't ask you that, but if I had, that's how you would deal with that. So now that we have the parameterization, it's not too big of a deal to find that standard normal vector. We'll need to start by finding what's ts and tt, and that's just taking the derivative in respect to s and then in respect to t. So if I take the derivative in respect to s, we'll get 2s, we'll get 3 cosine of t, and we'll get 1/2 sine of t. And if I take the derivative in respect to t, then we'll get 0. This here will be negative 3s sine of t. And then we'll have 1/2 s cosine of t. And then my standard normal vector is going to be ts crossed with tt. So we'll have 2s here, 0 there. We'll have 3 cosine of t. We'll have negative 3s sine of t. And then we'll have 1/2 sine of t and 1/2 s cosine of t. So what does this get us? In our I component, we'll have 3/2 s cosine squared of t minus 2s times 1/2 s cosine of t. So that's just going to be s squared cosine of t. Oh, never mind. I thought that looked wrong. Let's try that again. That was the j part going the other way. So the I part, yes, 3/2 s cosine squared of t, and then plus 3/2 s sine squared of t. Yeah, usually you can expect some Pythagorean identity stuff to happen with these. So that was kind of a clue that something went sideways. For goodness, I know my letters. For j, we'll have 0 minus, we'll have 2s times 1/2 s cosine of t. That's the one that I said earlier. That's going to be s squared cosine of t. And then for k, we'll have, that'll be 6s squared sine of t, or actually negative 6s squared sine of t, minus 0. So that gives me as my standard vector, this will just turn into 3/2. This will turn into negative s squared cosine of t. And then this will turn into negative 6s squared sine of t. It's worth trying to think which way are these vectors going to face. And I think we can see that they're probably going to face inside the paraboloid, because here I have cosine, but now I have something, so cosine's this point, but then I have a vector that's pointing in the direction of negative cosine, pointing in the direction of negative sine. So they'll be pointing inside the hyperboloid. So there we go. There is our parameterization of this shifted paraboloid.